Good morning, ladies and gentlemen, members of Cambridge Society, friends of members of Cambridge Society. Thank you all very much indeed for attending today. This is, of course, the second in the series of Cambridge Cutting Edge Lectures, which the Cambridge Society of Paris started earlier on this year. We are hugely lucky to have an absolutely outstanding speaker, and it's my role at this particular moment to introduce you to Professor Sir Roger Penrose. In doing so, I'm supposed to introduce and tell you a bit about Professor Penrose. The second part I find some difficulty in doing. It is very complex. I can tell you for a certainty that he was born in 1931, that he was born into a remarkable family. His father was a psychologist and a geneticist. His grandfather was a physiologist. His grandmother was Russian and left St. Petersburg in the 1880s. He had an uncle, Roland, who was married to someone who was a great icon in Paris in the 1920s, muse of Man Ray, photographer Lee Miller. His brother is another physicist, and indeed he has a second brother who is a chess grandmaster. So a remarkable family. Professor Penrose first of all studied at UCL, and then did his PhD, completed his PhD at St. John's College, Cambridge, of which I see certainly some members here. But in fact, unlike most people, he's actually attended, been involved with 7 academic institutions. He has also won many, many prizes. Google listed 14 as a minimum, including the Wolf Foundation Prize. He's a member of the Fellow of the Royal Society. He won the Edison Prize. He won the Albert Einstein Medal, and so on. At least 14 major prizes. He's written 5 books, 3 books in collaboration, 2 of them with Stephen Hawking, 3 academic books, and numerous other publications. Now, 5 books doesn't sound necessarily that many, but keep in mind that one of his books, The Road to Reality, is as long, almost as long as War and Peace, and whereas Tolstoy wrote in Russian, Professor Penrose wrote in mathematics, 1,099 pages, complete synopsis of all the laws of physics. On Google, they remarked on 26 subjects for which he is unique, outstanding, and of world importance. Those included twistor theory, spin network, black hole bombs, and so on. Now, to me, a simple land economist from Magdalen College, Cambridge, those are words. Beyond that, I could scarcely comprehend the greater detail, and hence beginning off by saying I was going to struggle to introduce what Professor Sir Roger Penrose does. What I will do is just briefly recount, as a more sort of anecdotal subject, meeting Professor Penrose at the Gare du Nord yesterday. His secretary wrote to me with great pride saying she'd booked him onto the first carriage, carriage number 1, so there'd be minimum walking, so he'd have no problem. Unfortunately, carriage number 1 happened to be the very furthest at the Gare du Nord rather than the closest. I pleaded with the controller from SNCF to allow me to go onto the platform to assist with luggage and so on. SNCF are not known for their pragmatism. So I waited at the barrier, and Professor Penrose was the very last person to come through because he'd been in the very furthest carriage. He's, I think it's fair to say, probably older than anyone else in this room, but nevertheless, he was carrying a large backpack, suitcase, striding out like a man of 20 with a purposeful look in his eye. We got into the taxi, and normally on those sorts of occasions, one bemoans the latest strike by SNCF, one talks about an incredible amount of rain that's been in London and so on. One might even mention the B word. This occasion was very, very different. In the 10-minute journey, plus another 5 minutes because the taxi driver got the wrong address, so in the 15-minute journey, I heard about universities, multiple universities, eons as I was told to call them, the fact that twice over one has been able to hear an echo from the latest Big Bang, all those many, many years ago. He touched on human consciousness. He touched on what happens when you're under a general anesthetic, but your consciousness goes, but your body otherwise is totally the same. What has disappeared? If you can turn it off, can you turn it on? And he talked about microtubules, in which perhaps quantum memory remains even after death. So it is possible that memories can remain in their peculiar fashion even after death. All this in a 15-minute taxi drive. We are in the hands today of a very, very, very unusual and exceptional person. Professor Sir Roger Penrose is one of the world's greatest living scientists. In an hour's time, we will all go back on the streets of Paris. We'll be walking amongst people who are thinking about their mortgage, what they're going to eat for dinner that night, whether their children have passed their latest exams or whatever. For the next hour, we're going to be in a totally different realm. We're in the realm of someone who is one of the very few people, along with Stephen Hawking, Albert Einstein, who has unraveled the intricate mathematical details of our planet, our universe, and previous universes. Professor Sir Roger Penrose lectures all around the world. We are very, very lucky today to have him. I'd like to thank the Conservatoire, from whom there's a notable lack of their students. But I'd like to thank the Conservatoire very much indeed for allowing us to be in this amphitheatre. I would like to thank Terry Quinn for introducing us to the Conservatoire. Terry tells me as a detail that he passed his doctorate here with the Garde Républicaine lined up behind him to make sure that he properly passed his doctorate. So at this point, with just one little quotation, which I'd like to add in, attributed to Roger Penrose, who apparently said, "This universe is here more than just by chance. There is a purpose. There is something deeper beneath it." And with that, I'm going to leave you and hand over to Professor Sir Roger Penrose, what I know will be a very, very intriguing talk. Thank you.
Well, thank you very much, Andrew, for that over-flattering introduction. It's a very great honor for me to be here and in this very distinguished room, and in the invitation by the Cambridge Society, and I apologize for the Oxford that I'm attached to. But as you explained, I had... I see. Right. I had connections, certainly with Cambridge also. Anyway, so I want to talk about what I've christened as Hawking points, and I have to tell you what they are. I claim that these are things that if you could see the world with microwave eyes, then you could probably see them. But I'll have to come to what it is that they are, and that's the talk will... Well, I have to get this thing working and make sure I can manipulate the slides properly. Let me hope that that works. Yes. First of all, I want to talk about the universe as a whole. Now, the universe as a whole, that means space and time. And this picture is supposed to represent, there's the Big Bang at the bottom. Time is going up the picture. You must think of sections through this. Let me see if I get this thing to work properly. Yes. A section through that represents one moment of time, if you like. And that, you think of that plane as moving up, and the section, you see, it's just looks like a curve as the intersection, but you have to think of that as 3 dimensions of space. So the whole thing has 4 dimensions, although it's just represented as a surface. So I've suppressed 2 spatial dimensions. So if I draw the curve round that this plane intersects the figure as, is meant to be space at one moment. Now you might ask also about what all the frilly stuff is at the back. That's because I'm not trying to prejudice the issue as to whether the universe is spatially closed up or goes on open to infinity. So I don't care about what happens at spatial infinity. Could be one way or the other. And to illustrate the different possible kinds, I hope I get this right here. Here we go. The different possible spatial geometries. It could be on the top right, we see a Euclidean space. I'm using these illustrations due to the Dutch artist M.C. Escher, and he very beautifully illustrates the three types of spatial geometry. The Euclidean geometry, which is the flat one at the top left, and then it could be sort of folded up like on a sphere, which would be the top right, or could be what's called hyperbolic geometry. I'll say a little bit more about this picture at the bottom later on, because it's important to what I want to say. But with regard to the spatial geometry, I'm only just illustrating these are the three basic types of geometry you could have, and we don't really know which it is. People often argue that it's the flat case, but that means because if it's one of the others, the radius, if you like, of the sphere is so big that they haven't got a good measurement of that. But as I say, it doesn't make much difference to my talk, so this is only just to tell you the alternatives that there might be. And let's go back to my picture with its sort of frilly stuff at the back, which is saying, who cares? Of course, I care, but it's not important for my talk. Okay. Now, the other thing I want to say about the picture is if you were a professional cosmologist, you might say, well, it doesn't illustrate an important thing which is supposed to happen at the Big Bang. You see, the Big Bang is this sort of thing at the bottom, which is supposed to be the origin of the universe, this huge explosion which originated the universe. And what current cosmologists would say is there's something called inflation. And inflation is not illustrated in this picture. Well, there are two reasons why it's not illustrated in the picture. One is maybe it is illustrated, and it would be right in the black dot at the bottom, so you wouldn't actually see it. So let's have a look at the black dot by bringing in a very powerful magnifying glass. There we are. And that very powerful magnifying glass will have a better look at what's going on according to inflation at the Big Bang. And here we have it. The thing at the top right, I should explain, is the handle of the magnifying glass, not anything to do with the universe. So the main point I want to stress here is that this inflation looks very much like the remote future of our universe. It's what's called an exponential expansion. Exponential doesn't just mean very big, it means self-similar, so that the rate of expansion is proportional to the size of it. So it's sort of, if you use a magnifying glass at the remote future, it would look pretty well the same no matter how powerful your magnifying glass is. So that's what exponential is. And so the thing is that the Big Bang, near the Big Bang, I should say, this picture here, according to inflation, you have another phase of exponential expansion. When I first heard about the inflation scheme, I thought it wouldn't last a week. I was completely wrong. It's still going on, and cosmologists will swear to it that they have to have this inflationary phase at the universe. It's a very artificial theory. It's dependent on a sort of potential function which you more or less draw by hand in order to make it do the things you want it to make it do. But nevertheless, it's there for a reason. It wouldn't just be a whim of cosmologists. They wouldn't have a thing like that if there wasn't a good reason for it. And this has to do with the microwave background. I'll come back to the microwave background shortly, but it has a certain characteristic, which is that it's scale invariant. You magnify it up, and it looks just the same. And that's something that you have to have a phase in the universe with this exponential expansion in order to make sense of the way the microwave background works. Now, I have to remember what my next slide is here. You see, one of the reasons that inflation was introduced was that the universe is very, very uniform. I'll come to that later again too, but there are all sorts of irregularities. You see galaxies and clusters of galaxies and things like that. But on the whole, it's very, very uniform, spatially uniform. And one explanation for that was inflation. So the idea is it might be very complicated to begin with, but as the universe expands and expands and expands with this inflationary phase, it stretches it all out as sort of pretty well flat and very uniform. And that was one of the reasons for inflation, and it's one of the reasons that people are very reluctant to give it up. But I never believed this. And now let me give you my explanation for why I never believed it. Let's suppose that I should say there's a thing called the inflaton field, which, as I say, it's the thing that you have a potential function which you draw by hand. It's invented in order to make inflation work. This inflaton field, I won't explain what it is or anything, except that it's supposed to be what makes inflation work. Now, let's suppose that the universe was contracting and not expanding. So I should explain that the equations of Einstein don't prefer one direction of time to the other. So if you reverse the direction of time, Einstein's equations are completely unaffected. That's with the inflaton field or without the inflaton field. It doesn't make any difference. All these things are time symmetrical. So that if the expanding universe is a solution of the equations, then so also is this contracting universe. Now let's suppose the universe was contracting. And let's suppose also there were certain irregularities in that. And these irregularities would involve sort of galaxies or something. And these would also involve the production of black holes. I'll come to black holes shortly. But these black holes would sort of collide with each other. And as you get closer and closer to the top of the picture, in the remote future in this picture, they would all congeal with each other and make one incredible mess. And nothing so nice as the picture that I have here, but something much more like that. Some horrible mess would be the generic collapse of all these black holes and all the stuff there is in the universe. Now, if that is a solution of the Einstein equations, and a much, much more likely one, far, far more likely, then why was, now let's see if I get this working here, why was that not the origin of the universe? Inflaton field or no inflaton field, that is much more likely. And you might ask, how much more likely? How much more likely is that than this? Okay, how much more likely? Well, think of, I'm going to give you a number. 1 part in 10 to the power, 2 10 to the powers there, 124. You see, how many zeros is that 10 to the power? Well, you see, how many zeros is it? Well, it's 10 to the power 124 zeros. So if you wrote them down, it wouldn't go shooting out the room and way out to who knows where. So that's a big number. And that's how unlikely this, well, sorry, I'm going the wrong way. How likely this is compared with this. So inflation doesn't explain it, because this, as I say, is just as good an equation, a solution of the equations with the inflaton field in it, as is this. And it does not explain why the universe was nice and symmetrical like that, rather than the great mess like that. So this was one of my reasons for not believing in inflation. Now, there are other reasons that people like to have inflation. And the reason that it didn't die at birth or within a week is that it explains something. It's the only explanation people could think of for the scale invariance of the microwave background. I'm not going to go into that because it doesn't feature in my talk particularly. I'm just explaining that it's an important feature of this microwave radiation. I keep talking about the microwave background. Let me explain that. It's the discovery of it won the Nobel Prize twice, so it's pretty important. The first time was the actual initial discovery, which was Penzias and Wilson, and they had a device which they were set up for some other purpose, and they found this sort of crackle which was going on all the time. They found there were some pigeons nesting in the machine, and they thought maybe it was that. They had to clean the pigeons out, and it was still there. And this was this radiation coming in from all directions. Now, the microwave background is very important to what I want to say. It's actually central to what I want to say, but we will talk a little bit more about that later. But it is this radiation microwave, so think of your microwave oven, the sort of radiation, that kind of frequency that's involved, and this radiation is coming in from all directions. And it's the dominant signal which is coming in, much more important than the stars, in fact. Let me come to that, though. Now I want to talk about this picture again. It's not quite the same picture I had before. It's another Escher picture, but it explains a little bit better the kind of geometry that's involved. This is called hyperbolic geometry, It's a kind of geometry in which you have more than one kind. If you have a point and a line in a plane, you usually think of there just being one parallel to that line through that point, if the point's not on the line. But in hyperbolic geometry, you have several parallels to it. That's a long story, which I don't want to go into. But just the kind of geometry here is illustrated. The main point I want to talk about is not the geometry, but the fact that Escher has very wonderfully illustrated what's called a conformal representation or a conformal map. Now, you see that these fish creatures, as you get nearer to the edge, they get smaller and smaller and smaller. But think about the eyes of these fish creatures. They're circles. Now, as you get closer and closer to the edge, I mean, you can't see them as you get very close to the edge, but I'll tell you that those circular eyes remain exactly circles no matter how close to the edge you get. That's a conformal representation. So it means that the shapes, see, you usually think of Euclidean geometry where shape and size is important. And you have a notion of congruent congruent triangles where they are exactly the same in the geometry. But in the conformal geometry, there's nothing to do with the size. It's all the shapes. And it's to do with infinitesimal shapes, or angles, if you like. So that the small shapes, no matter how close to the edge you get, the fish will remain pretty well the same shape. And the eyes will be exactly circular right the way up to the edge, even though they look as though they're getting smaller and smaller. But as far as the fish are concerned, the ones near the edge are just the same as the ones in the middle. So you have to imagine that this is an infinite universe here, but the creatures themselves, although they're represented as though they get smaller and smaller near the edge, they are actually in the geometry that the fish inhabit, they're all the same. So you have to imagine this infinite universe depicted in this rather clever way. It's a representation due to Beltrami, although it's got a lot of other names attached to it. Beltrami was really the first, and he showed how you could represent the whole hyperbolic plane in terms of this very nice description. Now, you keep this in mind. I'm going to use this now for the whole universe. But you see, now we have to think of the kind of geometry for the whole universe. It's not sort of Euclidean locally, it's what they call pseudo-Euclidean. And let me try and explain what that is. And that is, you have to think about the light cones. So let me tell you what a light cone is. At the top picture, I have a light cone drawn. On the left-hand side, I've thrown away one spatial dimension, so I've got two space dimensions and one time dimension represented. On the right-hand side, I've actually tried to draw all these dimensions. So you think of time progressing as sort of horizontal slices through that cone, and as time progresses, these slices get bigger and bigger. So this is supposed to be what light does. So if you imagine a flash of light at the middle, that flash of light spreads out with the speed of light. And this cone represents the flash of light spreading out. And on the right-hand side, we see the flash at the middle. The next moment, you have a sphere where the light has got to. The moment after that, you've got the blue one, and that's where the light has got to the moment after that. And those represent different slices through this cone. So the light cone represents the history of a light flash. It's got a past bit to it, so imagine light converging on that point, and then the light expanding outwards. Now the light cone is the most important part of the geometry of space-time. And the speed of light is supposed to be something that you can't exceed. You can't even achieve it with a massive particle. So massive particles never get up to the speed of light. So that the world line of a massive particle, so here we have a world line, that is the history of that particle. It's just a line representing its history. And it's always within the cone. So it's not exceeding the speed of light. Whereas in the first top picture, that's special relativity. The bottom picture is general relativity, the difference being that in general relativity you incorporate gravity, and according to Einstein's theory, gravity curves the space-time, and so I've drawn the light cones sort of tilting in various ways to indicate the curvature of the space-time. Now, the light cones represent most of the geometry. And when I say most, I'll try and explain a little bit more what I mean. Now, let me talk about the bottom picture first. Here we have time represented. You see, the light cone is just how light behaves. And if you write down the equations which describe the geometry, there's a thing called G, which is supposed to be the metric thing. I'm not going to go into this in any detail, but it's got 10 numbers to describe it. And that Einstein's theory needs these 10 numbers at each point, which describe what's called the metric. Now, 9 of them represent the light cone. When I say 9 of them, I mean really the independent ratios of the 10 components. So it's most of the information, 9 out of 10 of the components simply are where the light cone is. So what's the 10th? Well, the 10th is telling you how clocks behave. So here I have some clocks zipping along at different speeds, so they've got different world lines, but they go through the same point here. So you say they both originate at that point and they zip off at different speeds. And these little bowl-shaped surfaces represent the ticks of the clock. So the first tick, the second tick, and the third tick. And the ticking of the clock is the 10th component. So I want you to distinguish these two things. First of all, it's just the light cones. And secondly, it's the ticking of the clocks is the 10th component. And now let me tell you about clock ticking, because it's very central to what I want to talk about. On the left, we have the two most famous formulae of 20th century physics. One, of course, is Einstein's E equals mc squared. That tells you that energy and mass, that's the E and the M, are basically equivalent. The c is just the speed of light. That's a constant, so don't worry about that. Essentially, it's telling you that energy and mass are equivalent. So that's perhaps the most famous formula, 20th century physics. But even earlier than that, Max Planck introduced another formula, which was the basis of quantum mechanics, E equals h nu. H is another constant, that's Planck's constant, and nu is a frequency. So this is the top formula here. I think it's the top one. The top formula there, which is telling you that energy and frequency are equivalent. So now let's put the two formulae together. One tells you energy and mass are equivalent. The other tells you energy and frequency equivalent. So therefore, mass and frequency are equivalent. So that tells you that any stable, massive particle is an extraordinarily precise clock. Now, we know that there are incredibly precise clocks, nuclear clocks, well, atomic clocks and nuclear clocks particularly, which are extremely precise. And the precision of that really comes down to the fact that mass is equivalent to frequency. So if you have something which is a stable, massive particle, it is an absolutely precise, very precise clock. Okay, so that's what gives you the 10th component. The light cones are the 9 of them, and the clock is the 10th, and that gives you the structure of space-time locally at any point that Einstein uses, the thing that I call G. G mu nu, or GAB, or whatever you call it. Okay, now there's an other side to this coin. The other side of the coin is that if you don't have mass, then you don't have clocks, and you just have the light cones. Now, this is particularly illustrated by the famous equations of Maxwell. Maxwell introduced a really fundamental, he's not so well known as Einstein or Galileo or Newton, but his contribution was pretty well of the same class. He introduced these equations which tell you how electricity and magnetism behave, how they interrelate, and give you light, because the way that electric and magnetic forces interrelate to each other is described by Maxwell's equations, and this is how light is described. Not just visible light, but X-rays, radio waves, this whole spectrum, which was then discovered later to agree with Maxwell's equations. And these equations tell you very fundamental to physics, how electricity, magnetism, and light behave very, very precisely. But one thing that's important about these equations is that they are insensitive to the scale. So you can change the scale here and there in different places. You do what's called a conformal rescaling, if you like. and it doesn't have to be uniform all the whole of space. Maxwell's equations are completely insensitive to that. They don't care. In other words, light doesn't care. Photons don't care. Photons being the particles of light according to Planck's ideas, as further explained by Einstein. And so we have the fact that, as I say, the other side of the coin is that if you didn't have any mass, then you wouldn't care about the scale. You would just care about the light cones. And this is the important thing which I want to come to. Okay, now what have I got here? Now you see, this, on the left-hand side, we see just a smaller version of the history of the universe according to current physics. I have drawn in the inflation because maybe it's hidden in that little point at the beginning. And we have now, I've squashed down infinity in accordance with that Escher picture. Now, let me see, I lost track of where that was now. There we go. So you see I've squashed it down. I've squashed the infinity down now in the way that preserves the cones. So the squashing down, you see, I said it's conformal. That means that when you have small versions or bigger versions, they're completely equivalent. What it means in space-time terms is that the light cones are preserved. So if you don't have the clocks, you just have the light cones, then you can squash down infinity, as in the Escher picture, to be a finite boundary. And that's in the future. So we've got the infinity squashed down. And that's done according to the... okay. Now, physically, does this make sense? Well, you see, there is a theorem due to Helmut Friedrich. I'm not going to go into all that. But he shows that even if you have irregularities, as long as you just have massless things running around, photons or whatever they are, then you can always do this squashing down. So you can squash down infinity to make a finite boundary. You notice that I've just got the future boundary. It looks just like a line, but remember that that line is a three-dimensional space. So if you've got a three-dimensional space, that, if you like, is a time. That's time infinity, but that's the top part. And so you can squash that down, and there's no problem about doing that. Well, at least there's no problem if you only have massless things around. I'll come a bit to that later on. But the universe certainly is dominated by photons. In the very remote future, we will have just photons running around, and they don't care whether you squash the infinity down or not. The physics is completely insensitive to that.